Composite materials are engineered substances created by combining two or more constituent materials with significantly different physical or chemical properties. When these materials are combined, they produce a new material with characteristics superior to those of the individual components. The individual components remain separate and distinct within the finished structure, creating a heterogeneous material at both macroscopic and microscopic levels. The primary components are the matrix, which acts as the continuous phase, and the reinforcement, which is the dispersed phase. The matrix binds the reinforcement together, protecting it from environmental damage and transferring load between the reinforcing elements. The reinforcement imparts special mechanical and physical properties, like strength and stiffness, which enhance the properties of the matrix. First, fiber-reinforced composites. These represent the most important category of composite materials, where high-strength fibers are embedded within a matrix. The orientation of these fibers can be precisely controlled to align with principal stress directions, resulting in a highly efficient and anisotropic material. This means the material's properties are directionally dependent, allowing for optimized structural designs where strength is placed exactly where needed most. In aerospace, carbon fiber reinforced polymers are used for fuselage sections, wings, and tail assemblies on modern aircraft like the Boeing 787 and Airbus A350. These materials reduce overall aircraft weight, leading to significant improvements in fuel efficiency and range. The ability to tailor fiber orientations allows engineers to create structures that efficiently handle complex flight loads while minimizing weight. In automotive applications, glass fiber reinforced polymers are used for body panels, bumpers, and suspension components. High-performance bicycle frames constructed from carbon fiber achieve an optimal balance of extreme lightweight and high stiffness for maximum power transfer. Tennis rackets, golf club shafts, and hockey sticks utilize carbon and aramid fibers to provide strength, flexibility, and vibration damping tailored to athlete needs. Second, particle-reinforced composites. These contain dispersed particles within a matrix, where particles are generally equiaxed with equal dimensions in all directions. The primary strengthening mechanism isn't direct load-bearing, but rather the constraint of matrix deformation around stiff particles. Properties are generally isotropic since particles are typically distributed randomly throughout the matrix, providing uniform enhancement in all directions. A classic example is concrete, where aggregates such as gravel and sand serve as particulate reinforcement embedded within a cement matrix. The aggregates provide compressive strength and stiffness, while the cement binds them together into a cohesive structural material. This particle-reinforced composite forms the backbone of modern construction, enabling the creation of durable, load-bearing structures. In automotive tires, carbon black particles are added to rubber matrix to significantly improve strength, abrasion resistance, and durability. Silicon carbide particulate reinforced aluminum represents advanced metal matrix composites, offering increased stiffness, strength, and wear resistance. Cemented carbides consist of hard tungsten carbide particles bonded by ductile cobalt matrix, creating tools that are both extremely hard and tough. Third, structural composites. These are engineered on a macroscopic scale, combining different materials in specific geometric arrangements to achieve superior structural performance. Unlike fiber or particle composites mixed at microscopic levels, structural composites involve distinct layers or sections of different materials. The properties depend on both constituent materials and the geometric design of their assembly, focusing on optimizing overall structural response. Sandwich panels consist of thin, stiff face sheets bonded to a thick, lightweight core, typically honeycomb, foam, or balsa wood. Face sheets carry bending stresses while the core resists shear loads and provides separation, dramatically increasing flexural rigidity with minimal weight penalty. This design achieves exceptional stiffness-to-weight ratios, making sandwich panels ideal where structural efficiency is paramount. Aerospace industry uses honeycomb sandwich panels extensively for aircraft flooring, bulkheads, control surfaces, and engine cowlings. In construction, structural insulated panels with foam cores sandwiched between oriented strand boards provide both structural support and thermal insulation. Laminated composites built from multiple plies with specific fiber orientations create quasi-isotropic materials, or those tailored to complex stress states. Based on the matrix used, first we have polymer matrix composites. These are the most common type, utilizing thermoset resins like epoxy and polyester, or thermoplastics like PEEK and nylon. Carbon fiber reinforced epoxy and Formula 1 monocoques provides a lightweight, rigid, and highly protective safety cell, demonstrating polymer matrix composite capabilities. Glass fiber reinforced polyester for boat hulls offers excellent corrosion resistance and the ability to be molded into complex hydrodynamic shapes. Second, we have metal matrix composites. These use metal or alloy matrices offering higher service temperatures, greater toughness, and superior transverse properties compared to polymer composites. Aluminum reinforced with silicon carbide particles creates brake rotors with lower weight and better thermal conductivity than traditional cast iron. Continuous fiber reinforced metal matrix composites are used in gas turbine engines for components experiencing extreme temperatures and stresses. Third, we have ceramic matrix composites. These overcome the brittleness of monolithic ceramics by reinforcing ceramic matrices with ceramic fibers. Fibers act to bridge cracks as they form, deflecting their path and absorbing energy through fiber pull-out mechanisms. These materials are crucial for next-generation aerospace applications like combustor liners and turbine shrouds, operating at temperatures exceeding advanced metal superalloy limits. The classification of composite materials provides a fundamental framework guiding engineers through the entire product lifecycle from design to production. This systematic approach allows engineers to quickly narrow the vast field of available materials to candidates meeting primary performance requirements. Material classification directly determines viable processing routes, from thermoplastic forming to metal matrix powder metallurgy to ceramic vapor infiltration processes. Classification provides a common language for the global engineering community, facilitating collaboration and knowledge transfer across industries and applications. Knowledge gained from aerospace carbon fiber applications can be systematically adapted for high-performance automotive or marine applications. This systematic organization ensures past successes can be leveraged, failures understood in context, and the full potential of composites unlocked for future technologies. From fiber-reinforced to particle-reinforced to structural composites, each classification serves specific engineering needs across diverse industries. Understanding these classifications enables engineers to create lighter, stronger, and more efficient technologies, pushing the boundaries of what's possible. The systematic classification of composite materials remains the foundation for continued innovation in materials science and engineering applications. Want more composite materials insights? Like and subscribe today.